So for our speaker this morning, it's Lukáš Sekanina, professor here at FIT. Lukáš graduated PhD here at BUT in 2002, and he did numerous stays at good places like NASA Jet Propulsion Laboratory and Penn State and Madrid and others. He actually is now responsible for a group that is doing this evolutionary computing and bio-inspired computing here at FIT. He also serves the community as reviewer and organizer of many conferences. So I think like the speech guys are the most crazy organizers of events here, but closely followed by Lukáš. And Lukáš is also serving the scientific community here at the faculty. So if you ever decide to do PhD here at FIT, Lukáš is the chair of the Doctoral Studies Council, and he's actually ruling with tough hand over the quality and of PhD students, and we are actually sometimes complaining about it, but generally very grateful about it. Okay, so I give it to Lukáš. Thank you, Lukáš, for accepting to speak here, and the floor is yours. And the slides are in the shared directory, and I will complete shortly also the ones from yesterday that I still owe you. I think we don't have we have audio for the streaming, but we don't have like the amplification here. So if you don't hear properly, just move closer to the phone.
Good morning, everyone.
Good morning.
Thank you very much, Honza, for a kind introduction, and hopefully I will be able to tell you something which is relevant and interesting to you. Of course, I don't work on speech. I work, I would say, on machine learning, but also on hardware design. But maybe 10 years ago, I would not say that I work on machine learning, because it's a different area, evolutionary computing and genetic programming. But now it fits under machine learning as well, because genetic programming is a machine learning method. Do you have any experience with evolutionary computing or genetic algorithms or genetic programming? Is there anybody who tried at least? Yeah, maybe a few people. Have you ever heard about genetic algorithms and evolutionary algorithms? Yes. So if not, don't worry. Do you know what random search is? So it's very efficient algorithm, random search. For many problems, it's the best algorithm you can use. And evolutionary algorithms are also search algorithms inspired in biology, in genetics. And I'd like to show you how it's used not only for optimization, because in classic optimizations you have like 20 numbers and are searching for the best values for those numbers, but how it's used for design. So sometimes we want to design a circuit, sometimes we want to design a program, or sometimes we want to design a classifier. So why not to use genetic programming to do it completely for you, starting from zero? And I like to show you how we use it, especially for circuit design and also for design of neural networks in recent years. And it will be a combination of like explanation what genetic programming, especially genetic programming is, and something about our case studies where we have experience. Let me start with motivation. Motivation number one. Like 20 years ago, NASA was working on ST5 mission, small satellite. And one of the tasks was to design antenna. So here you can see small satellite. And this is a conventional design of antenna. Are there any antenna guys? I do, yes. Oh, one. Oh my gosh.
I used to be a guy 30 years back.
Because I just wanted to say it's just a wire, nothing, just wire. But what they did. So what they did, they used genetic programming not to optimize antenna, because maybe you know that genetic algorithms are used to optimize antenna, to find parameters of antenna. But they designed the antenna from scratch And here are the results. So completely different shapes than we have ever seen in the past. And such things went to space because it provided much better properties, radiation patterns, and also design time was much shorter than when you employ an expert on antenna design. And it was huge motivation for many people for doing automated design using evolutionary algorithms. So we wanted to design engineering objects, including programs, circuits, antenna, but also, for example, molecules or other stuff that engineers usually design automatically. And the benefits would be reducing design time and discovering completely new design that are out of the scope. Of course, it was 20 years ago. And everyone knows what happens in machine learning like 10 years ago when a new technology, slightly different technology, neural networks, were shown to do many interesting things, including automated design currently. My second example comes from my research group, where we design digital circuits. And if you consider a combinational circuit, logic circuit, you can see it as a program, right? It's basically programming. And this is actually design created by evolution, and it's approximate multiplier. So one of the area we work on is approximate computing. And here the task is to design arithmetic circuits, for example, multipliers or adders, that show some small error intentionally. But at the same time, they are much smaller and much faster than conventional designs. And then, if you are familiar with neural networks, you know that they are very error resilient. And if you use these approximate multipliers, for example, in machine learning applications or neural networks, you can get almost the same classification accuracy or your quality metric. Or maybe the user will not see any difference, but you can significantly reduce power consumption if you implement it on a chip. So one of the techniques are to optimize neural networks, especially for edge devices, is to use approximation principles, approximate memory, approximate arithmetics. And by means of evolution, we were able to automatically design approximate circuits, multipliers, showing great trade-offs between quality of output, which means small error, and power consumption and latency. And we use this technology, and I will show you it in more detail during the tutorial, to generate actually huge libraries consisting of thousands of approximate circuits. And then as a designer, you can choose the right one with respect to error, power consumption, delay with respect to your application. And you can download all the circuits in, for example, Verilog, C, or MATLAB, and get them immediately. So it was motivation. We can design something which other people are not able to do. At the same time, it's almost automatic. So in this tutorial, I like basically to do two things. The first one is to survey the basic principles of evolutionary computing with respect to automated design, and show you some applications from the area of circuit design and also neural network design. Case studies comes from a research group which is called Evolvable Hardware. The plan is to have a break in the middle, right, Hamza? Break in the middle.
Wherever you want.
As you wish, so as you are. And hopefully the slot will be used in reasonable way. Please just stop me if you want to ask. No problem, it's tutorial, so we can have more interaction. First of all, we will go into evolutionary algorithms, then how we use them to design circuits, and finally how it's combined with machine learning, because now it's a very popular topic, evolutionary machine learning, how evolutionary computing can improve machine learning, and on the other hand, how machine learning can improve evolutionary computing, and then some conclusions. Let me put together these two fields. Neural networks, where probably most of you are experts, because I guess almost everyone uses now neural networks for speech or natural language processing. And you probably know the history much better than I know. So for me, the biggest issue, or the issue, not the biggest even, was discovery of these deep neural networks that then were used in big applications. And then ChatGPT, but it started many, many years ago. Now, if you go to evolutionary computing, first method inspired in genetics were introduced in 60s and 70s in the US, and then later in 80s genetic programming. But these groups work independently of each other, and they didn't know about each other. And in the 90s, they started to communicate and created the umbrella term evolutionary computing. If you put together evolutionary computing and neural networks, you can see that immediately in 80s, they started to use genetic algorithms to train neural networks. So instead of gradient methods, they try to evolve, designed by evolution, the weights. It's a good method, but it's not scalable. I have seen a couple of papers in recent years where still they do training of neural networks using evolution. And in some application, it's possible even for complex networks, but definitely it's not the mainstream. Mainstream is gradient method for training. But where evolution is very good and competitive also today, is design of architecture of neural networks. So if you want to design architecture of neural network from scratch, evolutionary computing is one of competitive methods, including or in comparison with reinforcement learning and other methods. Of course, if you design by evolution topology, you can design weights together. So one of the first approaches where it is called NEAT, maybe you heard about that. And first work on evolutionary design of deep neural network comes from 2013. So I was supposed that it will be like around 2018, but already papers in 2013 appeared. And the last point that I want to emphasize here, there is initiative called AutoML, Automatic Machine Learning Zero. And here they try to use evolutionary algorithms to discover elementary principles of machine learning, starting from the simplest one to the most complicated ones. And they show that evolution can discover these principles from scratch. So one of the thinking in evolutionary computing community is, let's try to use evolution to rediscover what we have invented in past, and it was invented by greatest people in the field. So let's try to do it. And I will show you this thinking also in the other parts. And if you combine that with hardware, in 80s, people start to use genetic algorithms, not genetic programming, but just optimization algorithm for placement and routing for chip design. Around 1992, evolvable hardware was established, which is an area where people try to use evolutionary algorithms to automatically design, repair, and adapt hardware online. And is there anybody working on neural architecture search? Yes. So there is also a branch called hardware-aware neural architecture search. So you design not only neural network, which is good in terms of, let's say, classification accuracy, but which is also good for hardware. So you optimize the architecture of neural network, for example, for GPU. Okay, and it's called hardware-aware neural architecture search. I will explain it later. Now let's go to evolutionary algorithms. So I said that it's umbrella term for many different algorithms, and here I put the common features of all the evolutionary algorithms. They are search algorithms, so they work in some search space. And the first important thing is there is a population of candidate solution. So if you have random search or simulated annealing, you usually work with one solution and then do steps in the search space in order to find global optimum or minimum from one point to next point and then to next point. Here you have population. Population means it's a set of candidate solutions, which means that we can search in parallel. And this is a very significant property because it gives you a lot of opportunities in discovering not only the solution much faster, but also, for example, discovering all solutions, because sometimes there are many different solutions of the same quality to the problem. The second important feature is that if you have candidate solution and another candidate solution, and want to create next one, you apply operators inspired in biology. Mutation, crossover, selection. I will show you examples. So there are bio-inspired operators, how to move in the search space. Second, the third point is that we don't assume anything about the fitness function. We must be able to calculate fitness function for a candidate solution, but we don't suppose anything about gradient, for example. It has many advantages, but also big disadvantage. It's usually slow. Right? Evolutionary algorithm is a stochastic algorithm. So if you run it 10 times, you can get 10 different results. So very important thing is to do proper statistical evaluation of your evolutionary algorithm to be sure that the result is not just by chance. Okay? And as I tried to explain before, they are used to solve hard optimization and design problems where common methods don't provide good results. Okay, animation. Now let's start with the search space, and we'll say something about genetic operators and search strategies. Because I didn't know that we have antenna guys here, so my first case study is from antenna design. It's a very simple one. Let's say that we want to design a very simple antenna. And I use antenna because I had nice picture for that, so that's the reason why I use it. So let's say that we have two wires. I do apologize, wires. Okay? And there are two parameters that we want to optimize. Distance and the size of the smaller wire, reflector. Just two numbers. And antenna guys have developed a lot of interesting simulators. Basically, you set up the simulator and put two numbers, length and separation in this case, and it will generate a lot of interesting things about the antenna design, radiation pattern and so on, and one of them is gain. So you want to get good gain for your frequencies. And because the problem is small, what you can do, if you have a good computer, you can evaluate almost everything within reasonable intervals for length and separation. And what we see here is basically search space, right? And we can see that it's very difficult search space for search algorithms because there are many local and global local minima and maxima. And for example, the global optimum, the maximum gain, is very close to the worst possible solution. Okay, so common algorithms would usually stack at some local optima, and the task for evolutionary algorithm to find the best solution at a given time. So we are usually constrained by resources, so we have some time available for evolution. And we can easily say if we have maybe 256 options for length, 256 options for separation, the search of safe space, the size of the search space is 2 to 16, and we will see only those solutions. Maybe if there is a global optimum somewhere in the middle, we don't see it under this representation of the search space. So we should understand the size of our search space and whether by means of a given representation we really consider all reasonable solutions. Because in a wrong representation you can immediately lose a lot of solutions. Okay, so it's the point of, it's example of search space, and the goal is to maximize gain. And in our case, in evolutionary computing, the objective function that we want to maximize is called fitness function. In evolutionary computation, we maximize fitness. In general, in optimization, we speak about objective function. In training of neural networks, you usually speak about loss function, but the concept is the same. And a very important point, of course, I understand you are not beginners, but when I explain this to beginners, in real applications, we don't see this picture, right? In real applications, we have 10 parameters or 100 parameters or million parameters. In ChatGPT, 300 billion parameters. The task is to find the best suitable, the optimal values for all these parameters. And we don't see something like that. Okay, this is maximum, let's take this one, that's it. So that problem is difficult. What we do here is actually called black box optimization. We have a function, h, for example, here specified in real domain in n dimensions. We don't suppose anything about h, but we must be able to evaluate h. Okay? And we can introduce various constraints. For example, we don't want solutions where the x is between 5 and 7 or something like that. It's possible, of course. And one of the test functions that people use in evolutionary computations is this one for search algorithms. So there are competitions actually of search algorithms on a set of various mathematical functions of different difficulty. The task is to find optimum in a given time, and you are evaluated across of different functions, so you can get robust score for your method if you are good. Again, we can show the search space. We can easily optimize the global optimum. Visualize the global optimum. But please consider in real-world applications, another point is that, of course, okay, the search space could be relatively small, and maybe you can say, okay, let's evaluate all possible combinations. There are 60,000 combinations. But consider that to evaluate one of them takes 12 hours, or evaluation of one combination costs you $10,000. Why? Because one design point is one setup of aircraft, and you try to measure parameters or properties of a given shape of the aircraft and so on. You must put it to expensive simulator and so on. So it will be very expensive in real-world applications. And again, we have to encode somehow candidate solution. We have two parameters only. If we use binary encoding, I don't describe any binary encoding system right now, it's not important. But again, we can evaluate the size of the search space as before. I mentioned that there are different types of evolutionary algorithms. Genetic algorithms discovered or introduced by Holland at Michigan University are typically used for discrete optimization, scheduling, routing, because they represent candidate solutions as string of integers, typically, or bits. Evolution strategies were developed in Germany because they optimize wings of airplanes. And here, the typical application is numerical optimization. They use, these guys, these groups, use very similar principles coming from biology, but they use slightly different representations, slightly different operators. But in the 90s, there was unification. We will have evolutionary algorithms. We will meet each other because we are friends. They started to meet each other. By the way, they split into two main groups after some years. So now there is a group under IEEE. There is another group under ACM. And the overlap is not 100%. So some people goes only to IEEE conferences, the other only to ACM. In 60s, Fogel in the US designed automata. This branch is not very popular, but what's popular right now is genetic programming, where the main person here is John Koza from Stanford. And I will show you how genetic programming works, because it's used for program design, circuit design, and so on. And there are many other versions, and also algorithms that are similar to evolutionary algorithms, something like ant colony optimization or swarm optimization. And usually the comparison is usually a genetic algorithm against swarm, against ant colony optimization. So let's go to the main loop of evolutionary algorithm. I have for my students animation, so I will use the animation as well for you, but you are more familiar with more mathematical expressions, so you will have code as well. So we will have population of candidate solution. Let's say that the size of population is 6 individuals. We specify the size depending on the problem we want to solve. And the first thing is to initialize the population. Let's say we will do it randomly at the moment. We have to evaluate candidate solutions, so we apply fitness function to all candidate solutions, and we see that some of them are better, the others are not as good. Then we apply selection. We need parents for next generation of solutions. So selection works in such a way, typically, that, for example, we take 2 individuals from a population, compare them, and the winner will be parent. It's called tournament selection. Using this mechanism, we generate parents. Of course, we usually don't deterministically take the best one. We also take some, let's say, not well performing at the moment, because these individuals could contain genetic material which is very unique and can be useful to construct the final solution. And then the parents are used to create offspring. Crossover, you have two individuals and you try to swap some parts of their genetic code. Okay, these are, for example, bits, okay? So we swap some parts, so the first offspring will get the first part from first parent and the second part from the second parent. And the second offspring will get first part from the second parent and second part from the first parent. So it's called one-point crossover. And we do mutation. Here, in case of crossover, we can mix genetic material, but we don't introduce any new genetic material. But using mutation, which is a random change at a given position in the chromosome, by the way, we call it chromosome or genotype or candidate solution. Okay, so I will mix these terms. So we randomly change it here, and we basically create a new genetic material which can allow us to move from this point in the search space to a completely new one, which could be good. And then, when we have parents, we have offspring, we create a next population using some mechanisms. For example, we will combine parents and offspring together and select the best ones, or we can say that the algorithm will consider only offspring and so on. So there are many parameters, there are many options how to steer the evolutionary algorithm, and as a designer of evolutionary algorithm, we have to deal with that. Okay, to be more formal, we have to create population of candidate solutions. We have to evaluate them, and after evaluation, we can do selection. Without evaluation, no selection is possible because we don't know the quality of individuals. So we do selection, create offspring, using crossover, mutation, other operators, evaluate the offspring, and create new population using offspring and former parents. Typical parameters: population size, so how many guys should be in the population, how many runs of the generation process we should run. It's called the number of generations. Okay, one round is one generation. Probability of crossover, probability of mutation, and many others. How should we choose those parameters? Nobody tells you. Okay, this is a big problem in evolutionary computing. For toy problems, there are formal proofs regarding convergence. What's the best way how to do it? But if you try to solve a real problem, we don't have any such guidelines. It's based on experience and statistics. You do something, okay, maybe it can be better, but I have to properly evaluate it and compare statistical evaluation. So, let's say now that you want to use genetic algorithm to optimize your speech recognition model. And you can say, okay, this is my big speech recognition model, but I see here 7 points which can be improved because there are some constant, I don't know their values, so I want to set up them. So first of all, you have to identify what will be in your chromosome, so what you are going to optimize. So let's say that we will have 7 real numbers in our chromosome. In general, in applications, the chromosome can be string of bits, it can be string of integers, it can be vector of real numbers, but it can be also permutation. Any idea when permutation is good encoding? What kind of problems? Traveling salesman problem. So you have traveling salesman problem, 100 cities, you want to visit each of them once for each of them, and the natural representation is permutation, because you do permutation, and if you modify the permutation, you get another candidate solution. For genetic programming, our candidate solution will be syntax tree, or in general, some graph. Genetic operators. For bit string, everyone understands that the best way is just to flip a randomly selected bit, right? But for real vectors, consider that your chromosome is, let me put just 3 only. This is your chromosome. So the best way how to do mutation is not to work at the binary level. Because if you consider binary encoding of such number in a computer, it will be some floating point number on 32 bits, for example. And if you flip just 1 bit, you will completely destroy the number. It will be completely different. Okay, if you change 1 bit here, you can get 7 millions immediately, right? So what we do here is that we add a small number sampled from some distribution in order to change it only slightly. Because the point behind, or the idea behind mutation is to do small changes. Because if you do big changes, the algorithm will not be genetic, but it will immediately become a random search. Okay? Big changes means that you basically random search. Selection, replacement, I discussed that. Initialization. In most, well, in some applications we do random. We randomly initialize the values because we don't know what's the best way. Of course, we know that this first parameter should be from the interval -5 till 20, so we can use this knowledge. But generally, we don't know.
Talking of mutations, if your representations of permutation, what's a good mutation operator?
You have to ensure that the offspring is mutation again. Is permutation again. Yeah. And there are 2 approaches how to do it. You have to repair, right? So there are specific operators designed for permutations that generate valid permutation. So they do it in such a way that it's valid at the end. So it exists. And the second approach is to say, okay, I will not check it. I will use incorrect permutation as a potential solution. But if you calculate the fitness, you will see that there is a problem and the solution will get off from population.
I was also thinking it's the same about crossover. With
Yes.
mutation, I can imagine there are some
Yes.
permutation algebras and there might be a way to generate them sequentially or make one move in that permutation space. But crossover, again, I'm not sure how to think about it.
Yes. TSP, Strawberry Salesman Program, is one who's very popular for evolutionary computing, and they develop a lot of techniques how to deal with that. So it's of course, but very relevant question. In case of initialization, sometime, okay, I said we don't know, let's do it randomly. But in many cases, it makes a good idea to start with existing solution. So, for example, if you design approximate multiplier, as I explained at the beginning, we start with a conventional multiplier, and it gives, of course, solution much faster than if you start from nothing, right? Fitness function, very important thing. How you measure the quality of your candidate solution. It's not good to have fitness function in such a way that it tells you it's good or it's bad. You need some degrees. It's better than other solution. You'd like to measure differences. Parameter tuning, many parameters. What's the best setup? The only way how to get it is to try it. We usually do multiple runs with a given parameter setting. Create, for example, box plot. So let's say we have parameter set 1. We run evolutionary algorithm 20 times. We'll get some box plot. And then, let's say that here we had mutation rate 0.9. We do the same parameter setup. I will call it number 2, but the mutation will be 0.8. But technically, it could be completely different search algorithm because it will tend to do search in completely different ways. So you have to evaluate it against, here I said 20 runs. So here again you will do 20 runs. You will calculate your box plot, and then you can do some statistical reasoning about whether it's better that one or this one. Okay? And maybe under some statistical testing we can say it makes no sense, these 2 settings are the same under some conditions. Okay? And but if you read a paper on evolutionary computing and there is no statistical evaluation, you can immediately reject it. It's the first thing you do, actually. Not statistical evaluation. Goodbye. Okay. So far, so good. Makes sense, everything? Now, in real world, you don't want to optimize just one objective. Of course, in some cases, yes. Or if you use maybe gradient search, it's good for a single objective. But in reality, we have problems where we have to optimize several objectives. For circuits, you optimize functionality, delay, power consumption. And here we have the concept of multi-objective optimization. How many of you is familiar with the concept of Pareto front or Pareto dominance? I know expert on AI. Some those sitting over there, here. Okay. So if you have a single objective optimization, the best solution, the result, is a single solution. If you have multi-objective optimization, the result is not a single solution, but so-called Pareto front or Pareto set. What does it mean? Let's say that we have two objectives, F1, F2, and we want to minimize them. Of course, the best solution would be something here, but it doesn't exist. We don't have a car which is super fast and at the same time it costs zero. Okay. So if you run your evolutionary algorithm, you get different points as you can see here. What you want to eliminate in the first step are those that are clearly bad, because you have some guys which is clearly better. Consider solution A. If you check solution A against those crosses here, you can see that, alpha. Alpha, F1 is better for alpha than F1 for those crosses. F2 is also better for alpha than those crosses. So you can say that alpha is dominating those solutions, and you can safely remove them because you have something which is clearly better. But now consider blue guy, this one, and try to compare it against alpha. This blue guy, remember we have to minimize. This blue guy is better for F2, but alpha is better for F1, okay? And you don't know which one is better. So the situation is that you have, let's say, slightly more expensive car which is fast, but then you have slow car which is less expensive. What would be your choice? And we can say that we are not able to exclude those solutions because they are good at some point. And the result of multi-objective optimization should be a set of such solutions that are not dominated by any other solution. So we say that blue guy is not dominated by the other guys that are in circle, and also alpha is not dominated by the other guys. But we can safely remove the crosses. Make sense? Okay. This is concept of called Pareto front and Pareto dominance. And multi-objective evolutionary algorithms allows you to obtain Pareto front or something which is close to Pareto front, because maybe it's clear, but I didn't set it explicitly. These algorithms doesn't guarantee finding the optimal solution. Okay. In many applications, we don't know what's the optimal solution, but they try to give you with available resources close to the optimum, and here it's Pareto front. How can we solve it? The first approach is to transform the problem into a single objective optimization, because we know how to do single objective. And the second approach is very unique. I will explain on the next slide. So the first approach, how you can do it in a single objective setup, is using weights. Right? You have fitness function 1, 2, 3, n. You establish weights. Of course, the sum of the weights must be 1. You will minimize it. Let's say that it's a minimization problem. And the solution you obtain will be the result of optimization. You will get one solution. Maybe you can record some other solutions during optimization and just choose maybe some additional ones, but definitely it will not try to construct such a Pareto front. Here the problem is, for example, how to choose the weights, because in reality it's not clear. And also, in principle, some solutions are not reachable. It deals with the shape of the optimal Pareto front, and for some problems we are not able to reach it. I'm not going to explain it because it's out of the scope for today. The second approach is called epsilon constraint method, where basically we say we will accept solutions for criterion F1, for example, that are smaller than 5. And if the solution is smaller for F1 is smaller than F5, then we do optimization according to F2. So basically we fix one of the criteria and optimize according to the remaining ones. But what's very unique in evolutionary computing, and where evolutionary computing methods get a lot of points against gradient and other methods, is that they can design this Pareto front during the run, during evolution, can create, and at the end they will provide you the final set, and you can choose as a user what's your preferred trade. The concept, which is visible in several algorithms, where the most known is NSGA2, which means non-dominated sorting algorithm version 2, published in 92. Now we have version 3, which is for more objectives than 3 or 4. But when people use in real practice multi-objective algorithm, in most cases is NSGA2. How does it work? First of all, let's say that you have your candidate solutions, you have some offspring, you have some parents, and you do selection. So first of all, you try identify your Pareto front, which is this one here. If the goal is to minimize two objectives. And the filtering, basically we sometimes call it filtering, just trying to identify the Pareto fronts, is based on dominance relation that I just wanted to, that I explained to you on the previous slide. Individual x1 dominates individual x2 if it's no worse than x2 in all objectives and is better than x2 in at least one of the objectives. Okay, so you basically compare individuals, and according to all objectives, and if you are at least as good as the other guy, you are fine. And if you are better in at least one of the criteria, you can say I can dominate this. And then we create the sets of non-dominated solutions, and we can see several ones here. So we can say that x1 dominates that area, for example, x2 dominates the other area, and so on. Okay, makes sense, this approach? So it's like first step. So in NSGA2, we work in such a way. Let's say this is our population and our current population with parents, and here we have offspring. The goal is to create new population, and the size of the population is this one, like this top part. Okay, it's the size of population. And the question is how to select individuals from the set of parents and set of offspring to the next population. So first we put there all the individuals from the first Pareto front, from the best one. Then we remove the Pareto front and put there individuals from the second Pareto front. And at some point, let's say that it's Pareto front 3, we are not able to fit the complete Pareto front number 3 into new population, because some solutions, we can use, let's say 50, but now we have 60, okay? So then we have to choose from population, from NDF3, those that we will be used. And here we use heuristics called crowding distance. Basically, the crowding distance heuristics try to measure whether a given area around a given point is crowded or not. And we support those individuals that are unique in sense that there are not many other solutions. So it's formalized at average size length of the largest cuboid encoding the point without including any other point in the population. And we prefer those having good growing distance, and those are put into the new population. And based on these mechanisms, we are able to preserve solutions that are on the Pareto front, on the best Pareto front, and at the same time, we want to see them distributed across all the Pareto front, because the objective of multi-objective optimization is to give a solution showing different trade-offs. Now, questions to multi-objective of optimization of genetic programming? No, genetic algorithms. No, let's go to genetic programming. So we can say that genetic programming is machine learning method because it can automatically design a model which does, for example, prediction or classification. But it can be used for automatic design of programs or also other structures that can be represented in computers, such as circuits, antennas, and so on. Typically, these structures are executable. So you have structure, and in order to see whether it's good or not, you must execute it. Okay? Without requiring the user to know or specify the form or structure of the solution in advance. So we don't assume anything, just having data, and from the data we want to get a program or the model or a circuit. The algorithm, the search algorithms, I would say is the same as we saw before. Okay, it's nothing very special, but what's very special is the representation of the problem, and genetic operators define over the representation. So in original works, candidate solutions were represented using syntax trees, as you can see here, and they were represented, for example, in Lisp, which is functional language. In general, we can work on graph structures where we have graphs, connections, and the task is to design basically graph describing program or circuit. And we need special genetic operators to create a new tree as a result of mutation from the parental tree, for example. What's the fitness function in such a cases? In most situations, you have some data. I will show you example later. And for your inputs coming from the data, you generate the output by your candidate program, compare it against target output. So it's kind of semi-supervised learning because you need to know correct answers. But what you get as back from the algorithm is fitness. So it tells you whether you are good or not, but it doesn't exactly tell you whether you are wrong or not in terms of machine learning. And you try to minimize this distance or any metric that you specify. So it's way how we evaluate candidate solutions. We must execute them on some data and calculate single value out of that, which is typically, for example, mean square error or something like that. Mutation. Let's say that we have a program which is now very simple expression, and mutation can work in such a way that we randomly pick a node and replace the node by a randomly generated subtree. It's a basic version of mutation. Of course, there are other versions. In case of crossover, we have two individuals. We randomly select subtree in individual 1, the pink one, in individual 2, the blue one, and we swap them. We will get new solutions. Crossover here is in this, it's called tree genetic programming, is very important operator. Symbolic regression is the most popular application of genetic programming. Basically, we have data, let's say very simple data, X and Y, and we can plot the data, and the goal of evolution is to create expression which tries to fit the data, and we can measure the difference using some metric. It can be mean absolute error, it can be whatever suitable for a given application. To have it very simple, I use these differences of absolute values. So I will have a candidate program. Let's say this is my candidate program I generated maybe randomly. I apply the input data X into the candidate program, calculate the response, and compare the response against target value coming from the training data, and minimize and do the absolute value on the difference. Let's look at the program. You can see it's very strange, right? If 5 equals 5, then do something. Here you can have cosine x minus cosine x. It's typically what you can get from randomly created programs. There will be very strange constructions, never used by normal programmers, but it's way how evolution works. Okay, and by analyzing it, you can see it's basically some kind of sine function. It's not very good approximation, but it's the initial approximation we have. Why is it good to approximate data using genetic programming contrasted to neural networks? So first of all, we can use arbitrary set of functions to create programs. We don't have any requirements, except the requirement that we must be able to connect elementary functions together somehow. But we don't assume anything about gradient. We can have mathematical functions and logic functions together. We can have if then else construction. So whatever, right? So it's called symbolic regression because the result is symbolic expression. The second good approach is that we can easily optimize according to several criteria because, as I explained before, doing multi-objective optimization is very natural for evolutionary computing. We can easily handle constraints. We can easily say that I don't want this type of expressions, I don't want this type of data, or you can do whatever because it's completely under your control and the underlying model doesn't exclude basically anything. And finally, which is interesting, especially with the development of huge neural networks applied in let's say sensitive tasks, we are potentially able to interpret solutions much better than if you have a neural network with million parameters. So you can design expression which represents the data, and you see, okay, if I take this feature and subtract it from the other one, it makes sense in reality because of something. Okay? So it's very good. The main disadvantage is that it doesn't scale so well as huge neural networks. So it can be used for small and mid-sized problems, or in case that you have a lot of constraints. Expansive and stochastic.
So,
yes.
Can basically you addressed what I've written down, because this produces beautiful solutions, but you have these GPUs that have basically a couple of basic operations that they can do very fast and for billion parameters like matrix, vector, multiplication, and so on. So is there a way to kind of enforce these constraints into your genetic algorithm? I mean, like, not only like, for example, do not use like all the functions that you find in the function library, but use this limited set that is available on my GPU.
Definitely.
And still like respect some fetching constraints and like data block size constraints and everything.
Yeah.
That is
definitely, it's everything under your control. It's the main advantage. But the disadvantage is that it's not gradient based.
Yes.
So you have to evaluate each candidate solution. And I will show you, it's 10, right? So we still have time, but I see that my slide is 19 and I have 80 slides for you. And the end is about neural networks and such a technology. For example, at the end, you will see how machine learning model can be designed in such a way that you design the model, basically some expression, and at the same hardware together in order to maximize efficiency. Okay, but yes. Yes.
So, for example, in variational inference, the distribution is not tractable, but we still have like gradient-based methods to get get the minimum of the maximum of the output. Is there such like approximations or parameterizations that will allow us to use gradient-based methods with like together with evolution?
There are approaches. For example, if you consider syntax tree, you can say that the higher level of syntax tree is designed by evolution, but these smaller parts are optimized by gradient methods and gives you something which you combine on the top together. Okay, so there are such versions, but it's not covered here. Okay, it's let's say advanced topic. Thank you. What we see now here on those slides is history. What happened 20, maybe 15 years ago. And I'd like to emphasize that we see something very similar right now, but in a bigger scale and in media. 15, 20 years ago, it was for experts only, but now it's also for media because it attacks normal people. But at the time, papers published in great journals like Science and Nature, and they show that we are able to do genetic programming. If you give us data, we can fit the data. We can do it in a multi-objective way because we will show you different expressions. And they created a company with effective implementation of this technology. And they said, okay, it's used by thousands of users, including many top companies. And this technology can do things like, okay, let's say that you have a physical system, you measure data, and the technology gives you expression describing the physical system. So it can automatically discover a description of physical laws from pure data. And it has not been possible before. Now with neural networks we can do something like that. We can have model for such data, but at the end it will be hard to get the expression from huge neural network. So it was very, I would say, strong technology at some time, but as I mentioned, it worked for relatively small problems. Okay? And John Koza, one of the main proponents of genetic programming, said, okay, we can automatically design new inventions and we can rediscover patentable inventions or even create new patentable inventions. So he went to patents description, tried to extract specification what people wanted to protect by patent, and using this specification without any other knowledge, he ran the genetic programming system and rediscovered things that were patented by companies and also created new patentable inventions in analog circuit design. This is a sorting network, controller from automation, antenna designs. And in his book, which is genetic programming, and the antenna was one of them. And in his book, which is called Genetic Programming 4, it's fourth book by Koza. The first one, like 800 pages, genetic programming, describe the basic concept. But here it regularly shows, okay, domain by domain, I'm able to automatically create a human competitive results, most cases designs that were patented, and you can see examples here. At the same time, around 2004, he introduced competition called HUMIS, and the basic idea behind the competition is to evaluate whether a solution created by genetic programming is human competitive. Human competitive means that automatically created result is considered okay, the human competitive result, the criterion for human competitiveness is that automatically created result is considered human competitive if it satisfies at least one of the following 8 criteria. And there are criteria, for example, if it was invention in the past, or it's an improvement over a patented invention, or would qualify today as patentable invention, then you satisfy criterion I. Or for example, if it's equal or better to the result which was accepted by top journal, it's human competitive. Or if you win a competition, for example, some internet games against other strategies for solving some game, it's human competitive. And you submit your result created by Evolution to this competition, which is organized at the flagship conference on evolutionary computing called GECO. You submit the result, and there is a committee, and it evaluates whether you satisfied at least one of the 8 criteria, and there are some finalists, and then they find the winner. You can see the winners. The first winner was the design of the antenna for NASA ST5 mission we have seen before. But there are many other results in various types of scientific areas, like design of quantum programs, design of gain strategies, design of circuits, in algebra, and recently, for example, there was a paper published in Nature showing how genetic programming can do explainable image segmentation. So there are many strong results created by evolutionary computing in recent years combined with machine learning. And finally, before the final part of the talk on evolutionary computing, it was so impressive around 2008-10, these results, that patent lawyers started to think about automated creation of patents, that one of them, Robert Plotkin from the US, wrote a book, The Genie in the Machine, like there is a wish, your specification, I want to have a circuit which, I want to have antenna, I want to have classifier, and then if you have the genetic programming basis, then it will generate it for you. And he wrote a book about that and tried to analyze consequences for law. Okay? Does it mean that we don't need any patent office because everyone can do patentable inventions and so on? And he did an analysis from the point of view of law. And it's interesting that I just want to summarize in some way, and this is one of the reviewers of the book. And he said that we entered the artificial invention age, 2009, okay? Let's say dark time, winter for neural networks, where programs can automatically synthesize new products designs given only a description of what's required. What's the invention here? What's the invention here? Is it the new design? Or is it the program which is able to create this design? Or is it the requirement or the specification? And the specification in the book is called wish because of Genie. And which of these three should be patentable? And he said, okay, maybe it makes sense to give patents on specifications, because if you have the right specification, everyone can invent, if you have genetic programming with sufficient resources. I will go back to this slide at the very end of the presentation. Maybe, do you know what I mean, or what could be right now the wish? In case of the latest technology we have? Prompt. Okay, but it was 2009. Okay, the end of introduction to evolutionary computing. I spent first hour. So let's work on evolutionary circuit design. Do you want to break, or can I go with like 20, 30 minutes? Yeah, I would go and then do break around 10:30 or so, okay? Okay, so some slides which is interesting to hardware design people, especially people working on electronic design automation. Maybe not so much for you, but maybe it makes sense to give you a general picture. If you design a chip, there are many steps, starting from specification, design of architecture, speaking about digital chips like processors or so on, accelerators. Then you have logic design, logic synthesis, physical design, fabrication, packaging. What's very popular right now is to use machine learning across all the whole process. You probably know it's very expensive to design chip. That's the reason why we have only few big designers of chips, especially in Asia. And if you introduce a new process from 5 nanometer to 3 nanometer, it needs a lot of money. And if you design chip, you must have design which is perfect in sense of quality, no errors, and so on, because if you do mistake and generate millions of chips, it's very expensive. So they try to use machine learning at all the levels to get better results. And it's interesting that you can see papers in journals like Nature describing new technology advancements in this area. And at the same time, you can see that big producers using this technology. Let's switch to a different approach. Electronic design automation and evolutionary algorithms. It has been used, but it has never been visible. For some reason, people don't usually speak about the method genetic or evolutionary computing. In the past, it was a very sensitive topic for some people. That, okay, we use evolution, it's biology, it's not deterministic, we want deterministic method. Now it's much better with neural networks. People understand that neural network is AI. AI is good, so also evolutionary computing is good. But we know it's used at many places. For example, if you use NVIDIA cards, the transistors are optimized using evolution. So almost everyone using NVIDIA as a result created by evolution. And the first work on genetic placement of circuits on a chip comes from 1987. And if you go to hardware conferences, maybe more than 50% of papers deal with machine learning and different machine learning technologies, including evolutionary computing. And what do people use? They use multi-objective optimization because it's really needed in this area. They use these evolutionary computing techniques for design of hardware accelerators for deep neural networks because there are many optimization tasks you have to solve. For example, how to map your neural network onto hardware, in approximate computing, and in testing. So it was just a quick overview. And I'd like now to show you what we do here in terms of circuit design. Maybe you remember the results coming from Koza from the slides. There was almost nothing about digital circuits. And for some reason, he didn't report much in this area. And we started to work there and then created a technology how to design relatively complex digital circuits using evolution. So the basic scheme is, let's have evolutionary algorithm genetic programming, multi-objective. Let's specify data, basically, for the circuit. We want to get classifier, we want to get solder, constraints, objectives, building blocks, technology library. And let's run the system using different types of simulators and supporting tools. And let's create unique solutions such as approximate multipliers, approximate image filters, classifiers based on neural networks and others. And for them, we show good trade-offs between quality of result and hardware parameters such as latency, power consumption, and so on. But it's not only for this type of solutions. We can, for example, design Boolean functions that are interesting from point of view of cryptography because they have very specific properties. So there are many different things that we can do. So why? We'd like to create new design. We want to increase design productivity, and we want to take multi-objective approach. Problem number one is scalability. We can easily design small things, but the question is how to design big things. Of course, it makes no sense to design the complete processor, but we can design, for example, parts of accelerators. We can design arithmetic circuits, and there are scalability problems that we want to solve. And of course, trust. If you design by evolution, you get a result, but you don't know why it works. You can prove a lot of things about it, but in principle, you don't know the mechanism behind. So the question is whether you can use it or not. And we developed 3 strategies how to use evolution for design in this area. The first one is evolution from scratch. You start from nothing and want to design solution. The second we call genetic improvement, where you start with existing functionality. You want to protect the functionality. For example, you have multiplier, and at the same time you want to have exact multiplier. But you want to improve non-functional properties such as latency or area on a chip. And the third approach is evolutionary approximation, where in addition to improving hardware parameters, you can touch the function, you can slightly decrease quality, but to get great benefits in terms of power consumption and latency, for example. So what I mean by approximation? This is very simple 2-bit exact multiplier. It takes 2 bits, one operand, 2 bits, the second operand, and produces 4-bit output. Did you have digital design courses? Almost everyone, right? So, okay, so you can trust me that it can multiply. This is approximate version of multiplier, create manually, okay, not by AI. Some people just try to play with the design, and because design is smaller, they'll create approximate version. So you can see that the approximate version is correct, except the combination 3 times 3. And if you use this approximate multiplier, 2-bit, as a building block of bigger multipliers, you can introduce some errors, of course, but you can reduce power consumption by almost 50%. Okay? So it's idea. And the question is whether we can do such approximations automatically. Just say what you want and it will generate the result. So design automation methods in this area started around 2012. And in 2013, we first published a paper on evolutionary approach to approximate circuit design. And since that time, so we spent more than 10 years in this area, we generated technology which is able to do approximations that are under control, so you specify your target error, for, let's say, large-scale circuits. The version of genetic programming we use here is called Cartesian genetic programming. So now we have genetic programming, and we want to represent digital circuits at the moment at the gate level. You can see a candidate digital circuit. And in Cartesian genetic programming, we represent them using directed acyclic graphs in such a way that we have a 2-dimensional array of gates. And we specify the size, so the maximum size here would be 2 rows, 3 columns. And for each position, for each node, we specify its function. So there is a set of functions. So you can imagine a set of gates. And for example, AND is encoded using 0. For example, exclusive OR is encoded using 2. So for each function we have a code. And then we encode how the inputs are connected. So if, for example, 3 and 2 is here, we see that this guy will have the first input from the address 3, the second input from the address 2, and also all the primary inputs and all the outputs of the gates has some address. So we can simply specify functions and connections which defines combinational circuit. Make sense? At the end we have 2 numbers because there are 2 primary outputs telling us where the primary outputs are connected to. So using this simple scheme, we specify the maximum size of circuit, for example, 100 times 50 nodes. Then we have description of a candidate solution, and the task is to find the most suitable numbers here, so it's optimization problem, which represents a circuit. We use very simple algorithm based on mutation, so we don't have crossover. Why? Because in the field, nobody has ever discovered useful crossover for this representation. So mutation is the only operator. And the good thing is that we can use this representation not only for gate level, as you can see here, but we can play at the transistor level. We can play at the higher level of abstraction. For example, when we design image operator, the elementary operation is not AND and exclusive OR, but it can be addition, maximum, minimum, so high level functions. And finally, we can use the same representation to design our networks. Now the elementary operation will be a layer, type of layer. For example, there will be convolutional layer, or there will be pooling layer. And based on that, we can design neural network. So the advantage of this representation is very universal, and you just modify your set of elementary operations, but you can still use the same framework. Mutation. Let's say that we want to design full adder. Do you know what full adder is? Input A, input B, carry in, sum, and carry out. Okay? It can be specified using truth table. Let's say that this is a randomly generated circuit. We have the chromosome here. We can calculate truth table for it. And we see that there are 6 mistakes in the truth table. So in this application, the easiest way how to establish fitness is the number of bits that are correct in the output for all possible input combination. So basically you simulate the circuit for all possible input combination and see, okay, 10 bits are okay, 6 mistakes. Mutation, we randomly pick gene here and we change it. Let's say that this is number 3 and we modify it randomly to number 4. What does it mean? Number 3 tells you that the input of this gate should go to top left node. Now, number 4 means that you should go to this guy. It automatically means that, for example, this gate is eliminated, you will not need it. And if you analyze the rest, calculate the fitness, you immediately see that this solution is perfect, so it's correct implementation of full adder. So the mutation operator is very strong in this context. It can significantly modify the circuit, and that's maybe the reason why crossover is not needed, because crossover usually does huge changes in the circuit. So this is the basic approach. Now, the trick, what we have to do here, is to effectively evaluate candidate circuits. So suppose that you have a circuit and it's combinational, so no sequential behavior. And if you want to calculate truth table, so you have to evaluate all possible combination, it's exponential. And in reality, it works for circuits with up to maybe 15, 20 inputs. So in order to eliminate the problems, our team was the first one trying to use formal methods from formal verification to calculate the fitness. Binary decision diagrams. Who is familiar with the concept? Almost nobody. SAT solvers. Who is familiar with the concept? Almost nobody, maybe 2 people. Why? Because you are here mainly machine learning guys, probably more electrical engineering guys. But we also here do computer science, and in computer science we can do formal verifications and so on. So basically I can tell you that in mathematics we have very specific models, such as binary decision diagrams, different representations of Boolean functions, or we can transform the problem to some other problem, such as satisfiability problem. And using solvers that are available, we can quickly decide whether parent and offspring are functionally equivalent. So we have parent circuit, we do mutation, create offspring, and the first question is offspring the same in terms of function as parent? And the second, if not, what's the difference? So what's the distance? And these questions can be answered using these techniques much faster than using complete evaluation, all possible 2 to n functions. So here it's a discrete optimization. I guess you are more familiar with optimization based on real numbers and gradient methods, right? So here we don't have gradients method, but we have other set of tricks in our pocket. And of course, we have to evaluate hardware. So how do you evaluate hardware? So if you have circuit, you should build a circuit and measure everything. Takes a lot of time. Makes sense. It makes no sense to do it if you need to evaluate 10 million candidate designs. So we cheaply estimate parameters of circuits based on some heuristics. Okay, so we can cheaply and relatively well estimate, for example, power consumption. Let me skip this one and let me show you a real example. The specification is, let's design approximate multiplier which is circuit having in this specification 8 bits here and 7 bits here, and it will produce 15 bits at the output. It's multiplication but approximate. So we do accept some error. In this case, we accept some worst case error described as epsilon. So our error should be smaller than epsilon. And the fitness function is the cost of the circuit measured as size of the circuit. And because we know the gates included in the circuit, we know also the size on a given fabrication technology. We can estimate the size of the circuit as the sum of the sizes of the elementary gates. And we know that there is very good correlation between this size and power consumption. So basically we have very good estimate of power consumption. So it will be the cost. So we want to minimize the cost. We want the smallest circuit, but the circuit must have error smaller than a given threshold. And there is another interesting constraint. We want to get multiplication by 0 exact. So if one of these inputs is 0, the result must be 0. So we don't want to have any mistake in multiplication by 0. Why? Because then I will show that such a circuit can be used in neural network accelerators. There are many multiplications by 0. And if you see mistake in multiplication by 0, it will propagate through layers of the network and it will not work at all. This is extremely important trick that we discovered during some experimental work, but if you don't use this trick, you will not get reasonable approximate circuits. In this experiment, for example, we will generate 6 million candidate circuits during the run, and we will use simple mutation to create new designs. And of course, we can seed the first generation using existing designs of multipliers. So in literature, there are different multipliers, so we can use them as seeds. And at the end of evolution, we will get some solution, but of course the solution is not acceptable by hardware community because we have only evaluation based off this estimate. So we take this solution and put it to tool for design of circuits, and we go across the normal process design and measure parameters at the end from professional tool, but at the end of evolution, not for each candidate solutions. So what you can see here is the progress of evolution. This is generation. Here you can see fitness, which is the cost of the circuit, which is normalized. 0.1 is exact multiplier. And color is target error. So you can see that if the target error is small, the progress across the generations is relatively small. So you will get very good circuits in terms of small error, but the savings are about 20%. But if you say, okay, I want to do deep approximations, and for example, my error is according to this epsilon, orange epsilon, you can see that the approximation can be very strong, and you can remove maybe 80% of the gates of the original one, or redesign the circuit in such a way that it contains about 20% of gates, but still satisfies the specification. Because I said we should do some statistical evaluation, we can construct the results from 10 independent runs to show you that the runs are relatively stable, that they can converge. And a single run takes about 147 minutes on here I'm not sure whether I think it would be on a cluster. Makes sense, this setup and evaluation. Okay, so it's typical experiment what we do. And later on I will show how it's used in neural networks. And using this method, we generated library which is called EvoApprox. And the library contains many approximate others, multiplied, unsigned, signed, multiply and accumulate circuits, dividers and other circuits. So for example, in case of multipliers, 8-bit multiplier, it's our popular target. We have over 50,000 unique designs. They show unique properties, and some of the circuits are available on website, so you can see error according to different metrics: mean absolute error, worst case error, mean relative error, error probability. You see power consumption, area for a given technology, and you can download Verilog file, C file, MATLAB, and Python file, and use it in your experiment, for example, to build accelerator of deep neural networks. And this paper got, I can say, the best paper. It was actually Interactive Presentation Award at the DATE, which is one of the great conferences in our area, and it's our paper attracting the highest number of citations because people use it. Example, error against power consumption, and what you see, these gray points are multipliers. So we have many thousands of multipliers. So you can see many multipliers. And we included only subset of those multipliers into the library. So you can see this, we call it approx slide, these black ones that are on the Pareto front. Of course, we can compare these circuits against other designs that are typically small and available in a couple of instances, so not in thousands or hundreds. And it should be clear that if I take this guy, for example, here, and I change the metric from mean absolute error to mean relative error, now it's not on the Pareto front, right? Because it was optimized here and it's on Pareto front. But if I change the measure, it can now be not perfect design according to this metric. So the advantage of this library is that you can sort this table in such a way that you want to optimize according to this criterion and that criterion, and to find the best trade-off according to those two criteria. Okay, let me skip specific mutations for digital circuits. And it's great because I have perfect. So before break we will finalize this one, and that's it. Excellent. Now, recently, 1 year ago, a paper in Nature Electronics was published about design of classifiers, something which could be interesting to you, using basically the same technology as I described to you. They have a set of gates. They use evolution to put these gates together and create classifier at the gate level. What's a traditional approach? The traditional approach is to take a neural network, to implement the neural network in hardware and measure classification accuracy and measure hardware parameters. Or, instead of neural network, you can use some other machine learning model, for example, some decision trees and so on. And they showed, using the method, where you can see here, we have some specification, they have data, training data. They design basically using the same technique based on genetic programming. They call it in slightly different way, gate level circuit, and the circuit is then synthesized and the results are reported. So they show that for many simple classification problems, I'm not speaking about ImageNet classification, I'm speaking about smaller problems, usually available in those machine learning libraries where you usually start if you want to learn how machine learning works. So there are many classification problems. So they show that against different types of MLPs, multi-layer perceptrons, multi-layer networks, basically, multi-layer networks and others, they are okay in terms of accuracy, but if you compare hardware costs, because they implemented some of the models in hardware, you can see a significant improvement in terms of power consumption, simply because the model is created directly at the hardware level, not using hardware implementation of some mathematical model which is typically used. Why is it important for hardware people, this one? Because the technology for fabrication here is printed electronics. So it's not standard electronics, but it's printed electronics. And you typically will not classify ImageNet using printed electronics, but some signals from sensors can be classified from using printed electronics, then it makes sense. Break, or questions before break? If not, after break, we will talk about combination of machine learning and evolutionary computing, and especially in hardware accelerators for deep neural networks.
Maybe one,
yes.
Just a simple short question. What is the time-consuming aspect here? Is it just the number of generations, or is it some specific step that takes all the time?
The most important time is evaluation of a single candidate design. Okay, so if you are able to evaluate candidate design quickly, you can create many generations, and of course if you have more, you usually get better result. But at some point it starts to converge, so it makes sense to stop it at some point. So if you are able to quickly evaluate candidate solutions, then you can use this technology.
Another question is like, the trade-off between the population size and number of generations.
Yes.
Is that the thumb rule?
Yes, exactly.
Maybe square root of the budget you have? No.
Let's say this is your population size. This is the number of generations. And we call it the number of, let's call it number of evaluations. And this is basically your budget. Yeah. And it's up to you as a designer of evolutionary algorithm whether you will have bigger population and smaller generation, or small population and more generations. But you are basically determined by the number of evaluations you can do. For some algorithms, for example, tree genetic programming, where a candidate solution is syntax tree, usually use a huge population here, for example 1000, and do only maybe 50 generations. But when we use Cartesian genetic programming, we have very small population here. We can have maybe 5 only, but we must do many generations. I'm able to calculate it quickly, maybe this would be fine, okay? So this is for tree genetic programming, and this is good for Cartesian genetic programming, okay? Make sense?
And to me it sounds like how wide a net you want to cast, that's your population, and how much you want to search, so I guess.
If you have a toy problem, you can analyze it mathematically and to do proofs about convergence and so on. Yeah. But here, it's extremely hard to do something useful in terms of theoretical analysis. You basically don't have any clue how to do this analysis in a reasonable way. You're welcome. Break? 10 minutes or 15? What do you? Third part of the tutorial, which is on combination of evolutionary computing and machine learning, sometimes called evolutionary machine learning, and also I'll talk about neural architecture search and hardware aspects of those. First of all, in machine learning applications, we usually have some problem, and then we want to do some classification, prediction, such kind of operation. We have to prepare some data, we have to extract features, we have to create a model, we have to deploy it. It's a standard pipeline, basically. And we can observe that almost all the steps can be combined with evolutionary computing in order to improve them. For example, a typical application is used to evolutionary algorithm to select your features. You have 1000 features, and you do evolution in such a way that you identify 7 important features that gives you 99% quality. And So it can be used for feature extraction, selection and synthesis. It can be used for model design, genetic programming and design architecture of machine learning decision procedure, for example, or for neural architecture search. So it's one way how evolutionary algorithm can improve machine learning. There is also the other way, how machine learning can improve evolutionary algorithms. For example, genetic operators now are very blind. You just pick two guys and somehow mix them to create offspring. There could be machine learning models that helps you to it in a much efficient way to get offspring better than parents with higher probability. And this thinking both ways now is very important because people in evolutionary computing community recognize, okay, machine learning is so popular, we have to also contribute somehow. So let's do it in this way. And there is a first handbook on evolutionary machine learning, when you can learn quickly what evolutionary computing is about, what machine learning is about, and all possible interactions. And it's also documented by the number of papers and their citations in, I guess, Web of Science or somewhere. It's a very attractive topic right now for the research community. And maybe last year and starting in 2024, how to combine evolutionary algorithms and large language models. And again, there are both ways. We can improve evolutionary algorithm using large language models. For example, we can use large language models again to improve genetic operators. We can do, for example, prompt design using evolution for large language models. And we can do automatic design of large language models using evolutionary algorithms. So today I'm not going to speak about these interactions because it's a relatively fresh field with some promising results. What I can recommend is this very recent survey. So if you want to go there, you will see these two pictures and find your way how you will apply it in your research, because it's definitely something we will see in next years. Because you know that I'm interested in hardware stuff, so where we can use evolutionary algorithms to help for efficient implementation of machine learning. So you already seen that we can design elementary components of accelerators such as approximate multipliers, approximate or efficient multiply and accumulate units that are needed in accelerators. It's one direction. Then we can do, for example, evolutionary driven selection of the best components of a library for a given hardware accelerator. A lot of work has been done on mixed precision and in general quantization. So you have neural network, you go to hardware. Typically you train in floating point, but your inference must go on 8 bits or 4 bits. So here there's a lot of options. Then you have neural network, you have accelerator, how to map the neural network on the accelerator, weight compression, and neural architecture search, I will tell you. I know that you are speech guys or natural language processing guys. In our applications, we mostly work on image classification because it's a good hardware case study. And what I want to emphasize here is that if you consider ImageNet classification problem, probably everyone knows, right? Then the best neural networks that are able to classify this ImageNet are of course still improving. Maybe you remember these old models, VGG and maybe AlexNet at the beginning. But now we have solutions based on visual transformers and there is a significant increase in top 1 accuracy, right? But the problem is that these models are huge, so we can see the number of parameters, and typically if you want to get high classification accuracy, you must build a complex model. And at some point, people started to use neural architecture search, automatic design of neural network contrasted to human design of neural network. And you can see that this NAS method can create models that are small. So one of the biggest advantages of neural architecture search is not that they are able to create neural network which is good in terms of accuracy or the metric you are interested in, but that the model can be small, can be suitable for hardware. And these NAS, these yellow and green ones, you can see they are good in terms of accuracy, but at the same time they are much smaller than those created by human. Okay? So it seems that in combination in hardware, in combination with edge intelligence, it makes sense to think about neural architecture search because the models created by humans are usually huge and can be simplified. We could observe it also in LLMs, ChatGPT, huge one, and now we have many models that are maybe of the same quality, but much smaller. Right? We have different types of hardware for machine learning. Some of them is used for training, some of them is used for inference. In my case, we are interested only in inference hardware. We don't think about training at edge and so on. And the main characteristic is power you need to operate the model and the performance. How many operations can you do? Of course, we have to somehow define the operations, but it's not important at the moment. So what I want to tell you is that there are many different hardware systems that can run your neural network. Some of them in big data centers where they can do also training, this type of symbol. Some of them are for inference, typically here for edge, very low power. And you can also see arithmetic operations use them because in data centers you typically see floating point, 16-bit, 32-bit. But if you go to edge, it's usually fixed point on 8 bits or even 4 bits. And also we see some analog neural networks as well for very low power consumption, and a lot of emerging technologies based, for example, on memory stores and other stuff. So I just want to tell you that there are many options how to implement your hardware, especially for edge systems. And regarding LLMs, recent plot taken from literature, here on the horizontal axis, vertical axis is size, billion parameters, and we can see that from BERT, which is this one, after 3-4 years, we end up in huge models. Of course, they are much better, but the problem is the size of the models. And from the hardware point of view, we started to speak about memory wall problem. The problem is that if you consider memory in size of transformer or the LLM or the weight, grows exponentially, but this way, 410 times in 2 years. But if you look at the best hardware available, it's just twice in 2 years. And there is a problem how to process it effectively, and only some players can do it, right? Not everyone. Just the hardware aspect of the thing. Because I'm going to somehow focus on efficient processing of neural networks, which means that we have to say something about target hardware. So let me briefly explain how we execute neural networks in hardware. The first architecture which is used in hardware is called temporal architecture, and it's what you know as CPU or GPU. Basically, you have multiple arithmetic units, and if they compute something, they typically can put the result into local memory. And when it's used next time, another unit must fetch it. So there's a lot of interaction through memory. So you can work in parallel, but with a lot of interaction with memory, which is energy inefficient in terms of, it's energy inefficient. Of course, if you have a huge model, there are many weights, million of weights, it's impossible to have all the weights on the chip. They must be in external memory. And what you typically do, you just move some part of the weights into the chip, do calculations, and then store the results into the memory and take other parts. So the huge model, it can be for convolutional neural network or others, is not executed in such a way that you have everything on the chip, you do calculations at that time. You do it part by part, maybe layer by layer, maybe part of layer by part of layer, and so on the chip, and you do a lot of memory interactions. So in order to maximize efficiency in computing, you have to reuse data as much possible that you already have on the chip, which are close to the ALUs, typically in caches or your memory subsystem. So number one is to reuse your data as much as possible. These temporal architectures are used for training as well as inference. In case of inference, we typically use spatial architectures where we have array of processing elements, and elementary processing element implements multiply and accumulate unit. So basically you multiply your weight by activation and add it to your partial sum. And then the advantage of this model is that if you compute it somewhere here, you can immediately use it the next step by others. So it's not necessary immediately to go to memory. And that's the reason why these architectures, if you consider the same resources, the same power consumption, are more energy efficient. These architectures are implemented as specialized hardware accelerators by many companies, or you can design your accelerator on FPGA. Okay. Now, there are many strategies how to reuse weights, activations, and so on in order to maximize energy efficiency or to minimize latency and so on. I'm not going to speak about it. Just want to tell you that it's something what people have to think when they implement neural network in hardware or on edge. And it also tells us that some architectures of neural networks are better for hardware acceleration than the others. This is one of the first accelerators for deep neural networks called IRIS from MIT. It's university accelerator. The second version comes from 2019, the first one from 2016. And again, just to give you idea what happens at the bottom, because you are not hardware guys, I guess, here, so just to give you a feeling. We have the array of processing elements, as I told you, and there is some interconnection possible among them. Okay, there could be bus, there could be generalized network on the chip. You have some local memory here, and you have global memory outside the chip. If you want to read something from external memory, DRAM, to local memory, it takes a lot of energy. This is extremely important comparison shown here, telling us that if you do elementary operations such as addition or multiplication, it takes like 1 unit of energy. If you move data between elements, it takes like 2 units of energy. If you move data from local memory, it takes like 6 units of energy. But if you go to external memory, it takes 200 units of energy. And basically all the optimization strategies are based on this knowledge. Okay? Because you know the cost of energy for elementary operations you can optimize. Okay? And typically, if you have deep neural network architecture and you have accelerator, you need some specialized software which creates a plan of execution of the neural network on the accelerator. So here the idea is that the mapper, the tool which creates the plan, is like compiler. Your accelerator is like processor, and your DNN is like program. And for the program, you use compiler to create execution, so it's very similar. And of course, the compiler needs to know the architecture of the accelerator. And then, when you do a particle mapping of the neural network on accelerator, and there could be thousands of different mappings of a single neural network on the accelerator that can give you thousands of different energy profiles. So this is one of mapping, one of energy profiles, and we can see layer by layer for LXNet, very simple neural network, that, for example, most energy is consumed by convolution layers, fully connected layers, less energy. Register file, which means small registers around the processing elements, consume a lot of energy. So basically data movement takes a lot of energy. Arithmetic operations are not very critical, but in some cases, yes. And based on this knowledge, you can do optimization strategies. Okay? Makes sense, this global picture? Good. So, the first thing where you can use evolutionary computing, which is very natural, it's quantization. 32-bit floating point in your GPU or on your CPU according to IEEE 754. Norm tells you how floating point numbers are represented. And you want to play with, let's say, 8-bit numbers. So you must specify your encoding system for 8-bit numbers, whether you will be working on floating points or fixed point arithmetic, how many bits will be used for given parts of the representation, and so on. Okay, so you have to design it, and it's called quantization. Mixed precision quantization means that you will use different number of bits, for example, for different layers of neural network. Because some of them are more sensitive to quantization, then you will use more bits, but some of them are not sensitive and you can use only maybe 4 bits per weight or for activation. So let's say that we have some neural network, we have training process on GPU, and this is our accuracy that we get after some time. And then we use 8 bits only. We do some quantization according to some algorithm. And then implement it in the accelerator, n-bit accelerator. We typically run additional fine-tuning of the weights because the quantization typically introduces some error. Okay? So it's called fine-tuning. So you run training using some training data on your 8-bit precision to get, and it can sometimes happen that the accuracy is higher. It can happen for especially this type of neural networks and this type of problems. As I told you, there are many different mappings how neural network can be executed on hardware. And if you use 8 bits, there is huge number of mappings, but if you use more bits, the number of mappings could be limited because if you have bigger numbers, there are less options how to do everything, right? And one of the parameters that we will use here is called EDP as a hardware characteristic, and it's energy delay product. So you want to minimize energy and minimize delay at the same time to have single objective optimization problem as we discussed before. But if you do the accelerator implementation, let's say that it's possible, directly on 32 bits, typically the energy delay product is much higher. And there are fewer options, as I told you, how to map it. Okay, it's just illustration of the concept. So I will show you what we did in terms of mixed precision quantization. We tested between 2 and 8 bits per activation and weights. We used quantized neural networks. We used quantized overtraining. And we used the technique called bit packing because if you have, let's say, 4-bit weight, but store the 4-bit weight in 32-bit word, it makes no sense, right? So what you want to do, you want to put like 8 40 bytes into a single word in order to minimize memory accesses, because during one memory read you can get more weights together. Okay? It's called bit packing, this technique. And then we want to have automated framework which tells you how many bits per weights and maybe activations should be allocated per a given layer of neural network. And it can be based on NSGA2, a multi-objective evolutionary algorithm. And just to give you basic calculations, let's say that we have MobileNet as an elementary neural network, and we consider convolutional layer number 2, just one layer of MobileNet. We have number of bits for activation, weights, and outputs. And we have two accelerators, Iris and Simba is different. One, we see the number of mappings that we can do using a given number of bits. And we can see also the minimum energy delay product obtained during these initial tests. And we can see that when we reduce the number of bits per given item, we can see that the number of mappings is increasing because it gives us more options how to plan all the executions. Okay, but still consider this just only one layer. So you have one layer, and there are more than 100,000 options how to map the layer on the accelerator. So it's itself very complex optimization problem. And typically, if you have more options how to do that, you see better EDP, here as well as for the second accelerator. But here I don't speak about accuracy. This is just about energy if you invest a given number of bits to your implementation. Because, of course, you can expect some accuracy drop here if you go just for bits, right? I will show on next slide. So, encoding. I said for evolutionary design, we have to first encode a problem, then you can design genetic operators, your fitness function. So, in case of encoding, the MobileNet, the version we used had 28 layers, and we will encode the number of bits for weights and activations for each layer. So in total, we will have 28 times 2 integers, numbers that we will optimize. And for a candidate solution, we will analyze accuracy that we can obtain, and we will analyze energy delay product to optimize hardware. Okay, so there will be 2 fitness functions and how the framework works. So we start with the pre-trained network. We have some data set. We have some accelerator. What we can do, we can create initial population. What's a single individual? It's something like this. Okay, it's vector of 28 numbers, weights, not weights, bit per weight, and 28 numbers, bit per activation. So 56, so this is our initial, maybe randomly generated candidate solution. So we create population of those. We do quantization overtraining for a given number of epochs. Of course, how many epochs, again, research questions, whether 5 is enough or 50 should be taken, and so on. And we estimate hardware parameters for a given hardware setup. And in order to so, you must have suitable tool. So I will show you in a minute, we develop a kind of tool, which will tell us energy delay product, basically energy, latency, and so on. And then, based on the results, we do standard algorithm, NSGA2 algorithm, where we have some Pareto optimal selection, offspring generation, and so on. And at the end, we should obtain the Pareto flow. This is more, there are more details about the experiment. Let's skip it. It's not important for now for the explanation. If you want to play with hardware, one option is to do everything with real hardware, but it's very time consuming and not practical. So what people use are either hardware simulators or analytical tools that can do very precise analysis of a given neural network implemented on a given hardware. One of them is called time loop. It was developed at MIT. And basically you specify in some language hardware. So you specify one layer, you typically specify what's going there as a mathematical operations. And the time loop is connected with XLRG, which is another tool where you get elementary costs for elementary operations. So for a given fabrication technology, for example, 45 nanometer, you know the cost for addition and multiplication in terms of delay, in terms of energy, and so on. So basically, using these two things, you can estimate with very high precision energy profile of execution of a given neural network on a given hardware, and you can see how much energy will be needed for all multiply and accumulate operation, for registers that store the weights, accesses to DRAM, and so on. So you get a very nice profile of the hardware. The problem is that this time loop doesn't support mixed precision quantization, and it doesn't support approximate operations. So we spent some time and redesigned the tool to support mixed precision and also to support these approximate operations. And then the first kind of results from our experiments is when we do uniform quantization. We don't use this mixed precision, but uniform, which means that we will use 8, 7, or 6, or so on bits per weights and activations. So the first outcome, which is very natural, tells you that if you use 8, 7, or 6 bits, it doesn't have any impact on energy. Why? Because the arithmetic unit works on 16-bit. It's right here. Internally, the hardware is 16-bit, and if you have two, in 16 bits, you can put two 8-bit numbers, two 7-bit numbers, two 6-bit numbers, and there is no reason to use 6-bit or 7-bit in terms of savings of memory, and the cost will be the same. But if you can go to 5 bits, then it means that you can fit 3 weights into the 16-bit word, and then you see the reduction in memory, in energy. Okay, so you have to think how many weights you can fit into a given number of bits, and that's why we use this bit packing approach in order to optimize it. Then we run this NSGA2. This dark color is the last generation. This light color is the first generation. We can observe Pareto fronts, how they developed during evolution. So we start with this one, let's say, and we end up with that one. X-axis is energy delay product. Y-axis is top one accuracy. And we can see that the evolution leads to solutions showing high accuracy. So basically there is no impact on accuracy, but we can significantly reduce energy delay product if we optimize the number of bits per weights and activations properly. And you can see the initial randomly generated configuration, and this is the final configuration that we obtained. So we can see that for some layers, it's good to use 8 bits, but for many layers, it's just enough to use 2 bits only. And still you will get the same precision. Okay, so in this approach, once again, we didn't optimize neural network, we didn't optimize hardware, we just optimized the number of bits devoted to weights and activations, because if you minimize them, you can do bit packing, you can minimize the access to main memory, and at the end you will get improvement in energy delay product, and in this case the same accuracy. Make sense? So it's a typical application how you can use evolutionary computing in connection with neural network and hardware. And now the rest of talk will be close to neural architecture search and how it can be used in connection with evolution. So in conventional design of neural network is that you have smart guide and a lot of computing resources, and they together create architecture of neural network, which is trained, and you get the result. Okay? In neural architecture, and of course, once the architecture is created, you want to go for hardware, so you have the architecture, you train it, and then you do a lot of optimizations and implement it in hardware, but still the hardware architecture is the same. Okay? In case of neural architecture search, you try to replace the smart guy by algorithm, by maybe genetic algorithm, reinforcement learning, something like that, which is called neural architecture search. Neural architecture search generates candidate architectures. Candidate architectures must be trained, so you typically train them. After training, you on test data compute the final, let's say, accuracy if it's a classification problem. And then, when you are satisfied with the quality, you take the best one. If you connect here estimation of hardware parameters of implementation of a given neural network into the loop, you can do multi-objective optimization and optimize not only a quality of network in terms of accuracy, but also hardware parameters. And this approach is called hardware-aware neural architecture search. Again, we will use evolutionary algorithm to design networks. So first of all, we must be able to encode the networks. And there are many approaches how to do that. So the simple approach is something we have seen actually in Cartesian genetic programming. We have some nodes, we have some connections, so we can, for example, say that several numbers will be devoted to encoding one layer. So the encoding is usually done at the layer level. We have some operation, for example, number 1 will be convolution. There will be some parameter. 3 will mean that there will be convolution with kernel 3 times 3. Maybe max pooling will be encoded by 2. 3 will be the size of the window. And source 1, source 2 are where the operation gets its inputs. So using this way, you can design almost arbitrary architecture of neural network. The first approach, which is used in literature, is called microsearch, where you encode the complete neural network. All the layers. Of course, sometimes it makes no sense to encode or to try to evolve solutions for input and output, because you know that it always be there, and it makes no sense to touch it. So, but all the layers between input and output will be somehow encoded and will be designed by evolution. In microsearch, the approach is different. You somehow specify general architecture of your neural network, and you say it will consist of cells and some layers in between. And then you will use this approach to encode your cell. So basically you will define a very small network, typically consisting of 10 layers and so on. But you will reuse it many times in the final network, because we know from human designs of neural networks, deep neural networks, that there are some blocks that are used many times. Right? There are stacked blocks. So this approach can be used here. Very interesting encoding, not so much seen in literature currently, but in theory of evolutionary computing we can do that. Suppose that we will encode a program into our chromosome, and if you run the program, it will draw the architecture for you. So it will be a kind of indirect encoding. So we don't encode directly layer by layer neural network, but the program, when executed, will set up the network. In case of evolutionary computing, we have to initialize the first population by maybe conventional designs, or we can do it using random approach. Then we need to train the network using training data. We have to calculate, let's say, accuracy using test data. It takes a lot of time, right? Then we check the final condition. If we can continue with evolution, we select parent, do some genetic operators, obtain offspring, and for offspring we do again training and fitness, and repeat the execution of the main loop of GA. This is very time consuming, and that's the reason why the first evolutionary approaches used in this area were extremely expensive in terms of GPU hours, but they generated relatively interesting designs. Currently, yes, neural architecture says based on evolutionary algorithm is used, but with a lot of techniques capable of significantly reduce all this time associated. Still, I have some time. Let me give you an example of another interesting encoding, which is binary for these deep neural networks. Suppose that your neural network is composed of phases. This is one phase, second, and so on. And in phase you can use up to 6 nodes. And by evolution, you are searching for the connection of the nodes. By the way, the node can be some convolutional layer, pooling layer, or just from your set of layers. And here they invented very interesting encoding, binary encoding, just to simply explain. It's sequence of binary numbers, and if you are in node number 6, you know that your inputs can come from maximum 5 previous nodes, because the total number of nodes in the phase is 6. And basically this sequence of 5 binary numbers tells you whether first, second, third, fourth, and 5 or 5th nodes are used or not. So you can see that the first, third, and 5th nodes are used as inputs, the remaining are not used. And there are some additional tricks, whether there could be some skip connection and so on. But basically you encode the architecture using string of integers. And if you can use string of bits, and if you can use string of bits, it's usually very efficient encoding because it's binary level. And they define crossover over these operations. And intrinsically, if you have one parent and second of this type, they identify typical structures known from human neural network. This is sequential architecture known from, for example, VGG. This is dense network, another famous human design, and if you do crossover, you will get ResNet. So the interesting thing is that it makes sense here to do crossover over the bit strings, because in many cases it generates something where we know it makes sense. Okay? And this method was used in the second version with combination of other tricks. I'm just going to skip them, say a few words a minute later, to basically generate the best deep neural network, convolutional neural network, for ImageNet classification and other tasks in so-called mobile setting. And by mobile setting, it means that you have maximum 600 million multiply and accumulate operations per inference. So it's a constraint coming from typically mobile phones, where you have limited resources, and for one inference, you can do only a given number of operations. So under this constraint, they were able to beat anybody in terms of accuracy and latency. Okay? Now, hardware awareness. What does it mean? It means that in addition to obtaining accuracy as one objective, you try to get cost of the model. And of course, the cost can be very different. This additional metric, it can be energy, it can be area on the chip, it can be latency, but it can be also, in some cases, there are designs optimized for sensors or very, very cheap devices, very optimized for the size of flash, because you have weights on your flash memory, and the capacity is very small, less than 1 mega, for example. And so you are searching for such neural network, which is good in terms of accuracy, but at the same time you can fit it everything to very cheap hardware. And the point in hardware awareness is that it's neural architecture search reflecting hardware, but not optimizing hardware. So we designed such architecture of the neural network, which is good for a given hardware, for example, in terms of latency, but we don't open any additional search space. For example, we will not optimize the architecture of the accelerator, because in the next step, what you can do is neural architecture search with hardware co-design, where you optimize architecture of neural networks. You have to still find the weights, and at the same time, you optimize hardware configuration. For example, you say, is it better to have array 10 times 8 or 16 times 15 programmable elements in terms of energy or latency for a given neural network? What kind of mapping strategy, compilation of the network to hardware shall I use? How many caches, and so on. So basically you try to optimize configuration of hardware, which is the third search space where we do search. What's hardware configuration? You can see many things that people can optimize, and what kind of algorithms we use. Of course, for searching for weights, we use gradient methods, but for optimizing architecture of neural network and hardware configuration, people typically use evolutionary algorithm or reinforcement learning, even for hardware optimization, some classic integer linear programming, because they simply don't have any clue how to do it in a gradient way. And it was a paper in transactional computer-aided design showing that opening this hardware space can significantly improve the results. And just a small example, consider that you have neural network, you have hardware accelerator, you optimize accuracy and energy delay product, and you start here. This is your initial implementation, showing some accuracy and showing some energy delay product. Just by optimizing hardware, not touching architecture of neural network, you can do some improvements. Here you do some hardware optimization. Here you optimize even the compilation strategy, how to optimize mapping of the neural network on hardware. So you can still get some improvement, but you never touch the accuracy because the neural network is still the same. You optimize the hardware. But now you add to hardware optimization neural architecture search. So you try to optimize model neural network, and you can immediately see Pareto frontier with different trade-offs between energy delay product and accuracy. So it makes sense to do it, but of course it's technically very difficult because you have many spaces where you have to search to, and you need hardware experts to tell you what to do. And finally, it's very expensive method, this hardware neural architecture search, or even neural architecture search. So there are many tricks, and let me go there quickly, how to accelerate it. So basically, you can do some simplifications. For example, in order to get fitness, it's not necessary to train for many epochs. You can remove, so reduce the number of epochs. You can employ some proxy data and so on. What's very popular right now is to do surrogate models. You basically have neural network. You don't do training. You just put some information, some features from the neural network to maybe another neural network or some machine learning system, and it will tell you, okay, the accuracy will be 85%. It's very popular, but of course it takes time to prepare such proxy. It's sometimes called proxy. And you can do the same basically also for hardware. If you want to evaluate hardware, the best way is to build hardware, but it takes time. You have to measure it. I have already shown you that we can use analytical tools such as time loop, but again, we can use prediction models based on machine learning. So you put neural network parameters and train some model, and it tells you, for example, latency on a given accelerator. So this is our work of one of my students. He developed a neural network which can predict latency on Halo 8L accelerator, and this accelerator is attached to very popular Raspberry Pi hardware, and you can do neural architecture search with very quick estimation of latency. Let me, because we should finish around 12, right? So let me skip this part and finally tell you something about our experiments with neural architecture search and approximate computing. So in our work, we use Cartesian genetic programming for circuit design, right? But in Cartesian genetic programming, you can say, okay, my node will not be logic gate, but it can be neural network layer. So I have set of layers like convolution 3x3, convolution 5x5, and so on. And I can encode architecture of neural network in this way. So this is my chromosome or genotype. This is a representation in graph, and then it's translated to a neural network. So we can do that. And then we can do mutation, we can do other operations in the classic loop of evolutionary algorithm. And the first paper doing this approach was published in 2017, and they showed at that time on Cypher10 dataset we can get very competitive results with this method. And because we like CGP, we extended this method in such a way that we allow to use not only traditional convolution layers and so on, but also approximate layers. So basically the computation is not done using exact multiplication, but with approximate multiplication. And again, the task of evolution is to set up the neural network architecture and at the same time to choose from the set of different multipliers, approximate multipliers, the best one for a given layer. So in addition to definition of convolutional operation, for example, you have to specify the size of window and so on, we also specify which type of multiplier from the library is used. And it's task of evolution to select the right one. And we run NSGA2, we optimize accuracy, we optimize the number of parameters of the neural network, and also we somehow needed to estimate energy profile of the neural network. And here we did a very simple trick. We just measured the energy needed for multiplication in the neural network. So we didn't consider memory accesses and so on. So our proxy was the energy needed for multiplication. And remember, some multiplications are exact, some are approximate, so it's not very uniform. This is one of evolved neural networks for for Cypher10 classification problem. And it shows that this particular convolution layer uses, for example, multiplication, approximate multiplier with this label taken from the library, and selection of this particular multiplier was done by evolution. Okay? So in addition to design of architecture, it also selects the approximate multipliers. And we see again trade-offs between accuracy and energy of inference. here estimated as the energy for multiplication. And we can see nice trade-offs between these two objectives. And also we compare it against other methods, and we were able to see, okay, our method is able to find good architectures for hardware. And then it was necessary to validate whether this simple proxy for energy is okay. And for that reason, we did full model of the accelerator in time loop. And as I told you, we also extended this type loop to support approximate multipliers and mixed precision quantization, because the original version of time loop doesn't do it. And we can observe that the original estimated Pareto front coming from our simple energy measure, the green one, is very similar to the Pareto front measured using the, let's say, very precise tool. So basically in this experiment, measuring the multiplication energy needed for multiplication is good proxy, and we can use it. So it was one of our research papers dealing with hardware-aware neural architecture search with approximate multipliers. And that's actually basically what I wanted to tell you from the theory of evolutionary algorithms and applications in design of circuits and neural network. So let me conclude with a few slides. First of all, let's go back to genie in the machine. And in 2009, the question is, what's the invention here? Is it the new design, the program, the requirement called wish at the time, and which of these should be patentable? After many years, Robert Plotkin wrote another article now considering technology based on ChatGPT and similar. And he said, at that GP times in 2009, the wishes still took highly technical forms that only experts could write, such as fitness function. So at that time, okay, the tool was automatic, but the expert had to write fitness function in terms of minimize the distance between the pattern generated by my model and the target pattern. So a piece of code. Now, with ChatGPT and so on, we are seeing AI that can take natural language wishes. So in natural language, you can interact, and as a prompt, and we can do inventions. Of course, you can do inventions using genetic programming, but also now in many fields, I don't know what's case in your field, but at least in hardware, we see a lot of papers dealing with large language models for design of circuits, where people say, I want to design adder with inputs A, B, C, and so on, and show me code in Verilog which implements this design. And if you have, let's say, properly trained model, if your prompt is specified in a good way, now it can do such designs. And it's a hot topic, and we see better and better designs. I believe combination of evolutionary computing and LLMs in this area would help, because one of the things what you can do is to improve automatically your prompts by evolution, not only by human. So the term prompt engineering already exists. It's known that writing good prompts takes time and skills, and there could be business around selling prompts, as probably we can see right now also in this area. So I just wanted to demonstrate that before the age of deep neural network, we already had very powerful technology, but the technology wasn't able to scale up in such way as deep neural network, and of course it was invisible to normal people. Normal people who don't know anything about AI now speak about AI because they can hear it in media, it affects their lives. And even my daughter, 11-old year, yesterday had to write 4 good points about AI and 4 bad points about AI. Impossible, you know. In 2010, you have never heard about AI in the media. It was just for experts only.
Did ChatGPT write it for her?
It was not allowed. Concluding remarks. I think that there are many applications for evolutionary computing in engineering design across all domains. Electrical engineering, programming, material design, robotics, many applications. Evolutionary computing is good if the problem is of small or mid-size. If unique solution is expected, because if you need some normal solution, why to use these specific search techniques? You can usually get some solutions using other techniques, but they are not typically well-tuned. If you really need multi-objective optimization, then evolutionary approach is good. And potentially explainable solutions can be created. For example, you can constrain this search engine to create only expression that you are able to interpret or you understand. Of course, maybe you exclude solutions that are good, but you will get interpretable solutions. Evolutionary algorithms are not used as the only method when a big problem has to be designed or optimized. You typically use combination of evolution plus something, or exclude evolution completely. So, for example, big traveling salesman problem instances with millions of cities are not solved by evolutionary algorithm. They are solved only in case that the size is small. Other heuristics are combined together to solve the biggest instances. And also sometimes people don't like the randomness behind evolutionary computing, because consider that you are a company selling design tool, for example for hardware, and the tool is based on evolutionary computing, so you buy it, run it for your problem and get some result. And the second company run it for the second problem and get much worse result. It's something what you as a company selling tools for optimization don't want to see, because you can get some complaints. And recent approaches that I'm going to follow in few years, I think it's combination of machine learning and evolutionary computing in both directions, especially with LLMs. If you want to play with evolutionary computing and GP, some recommended tools, of course, you can easily find other, or the evolutionary algorithm is not difficult. So if you want to learn how it works, maybe the best way is to implement your own tool, of course. References. I use many references across the slide, so it was reference on bottom line, but here there are the things. If you look into them, you should see maybe 90% of material covered. And of course, I have to thank my colleagues in the research group who helped us to put together the results. And also, we are significantly supported by Czech Science Foundation. Recently, for example, we have project on hardware machine learning from automatic design to innovative and explainable solutions. So you could see sample of research results coming from the project. Thank you very much.
Big thanks, Lukáš, for
Thank you very much.
And questions, of course.
This is a more basic question, I think, but I just want to clarify the distinction between just like genetic approaches and then differential approaches, because it seems for me like when you're working like with deep neural networks, etc., well, everything's gonna be differential, right? Like, I mean, is it just a representation? As I understand it, like if it's something like vector-based or differential, you're representing things as points in the Euclidean space. But, you know, for genetic, you have like more flexibility in just a symbolic representation. But at the end of the day, you're doing the same operations. Maybe not implementing them the same, but like there's still gonna be like crossover or mutation or other noise like with vector-based approaches, right? I just want to understand that distinction better.
Definitely, if you want to have answer what's better, it requires a serious study. So, of course, if people present new neural architecture search algorithm based, for example, on reinforcement learning, or now very popular is use so-called supernets. I didn't have time to discuss it. Do you know what supernet is? It's a huge pre-trained network, and you just sample subnets of the network that are, and you can share the weights. So it's trained in such a way that you can share the weights when you take subset. Maybe the accuracy is not as good as for the whole network, but you just sample subnet. It's already well trained. You can do maybe some fine tuning, and you can search. You can very significantly reduce cost of search. And the methods are based on evolution and are also based on reinforcement learning. And I think that there is no clear winner at the moment. Okay, so if you are a fan for evolutionary computing, you will use evolutionary computing. If you are fan of gradient methods, you will know gradient methods because you know how to use it. Definitely, if you want to multi-objective, especially with hardware aspects, most papers what I have saw use evolutionary computing. But if it's not critical and you just target accuracy, you can get the same results much faster. That's for sure. Also, just to maybe tell the remaining people, the other people, I just presented the discrete optimization approach to neural network design, and the problem can be designed in such a way that it's continuous problem. So the design of the architecture is continuous problem, and use gradient method to get at the end using softmax function discrete implementation of the architecture. So both approaches are as possible.
Maybe I will rephrase the question that I was asking Lukáš during the break. And that was about the combination of the genetic algorithm with the gradient descent. Because to me, the mutations and the fusion or whatever you call it, the
genetic operators.
The genetic operators, they basically jump as crazy in the search space. So I was wondering if there is someone or some ways to combine it. Maybe we do some kind of local gradient search where you know where you are in the search space and you have an idea on how to construct the gradient, and maybe do some higher level jumps with the genetic stuff.
Yes, and the answer was yes, there are approaches. So basically, the resulting expression or program or model that should be the goal is composed in two ways. In the first way, at the low level, you have some features and you do gradient search and you combine them with the upper part to create a final model. So such approaches are available in the literature. And maybe if you know in Prague, actually the guy is professor also in Netherlands, Babuška, if you know Robert Babuška. He's one of the guys introducing and developing this approach. So if you look at his papers, you can see that. But where is it good? For classic machine learning. But if I design circuits, I will not be able to formulate the circuit design problem as a gradient search. It will give me kind of efficient circuits. So maybe in hardware we don't see so many approaches based on gradient in this setup. Bowels. Can you read bowels? It's lunchtime.
It's lunchtime. Okay, thank you very much.
You're welcome. You're welcome. Thank you.
Here is the one here. psal, že to nemůžeme dávat ven, ten tutorial. Nemůžeme? Bylo tam něco citlivého?
Ne, asi můžete.
Tak jestli můžeme, tak
Myslíš ten záznam, anebo ty slajdy?
všechno.
Mně jde jenom o to, aby mě někdo nenapadl, že jsem ukradl obrázek a neocitoval. Když to o tom jde, jinak tam nejsou žádné citlivé.
Já jsem